My name is Edwin Kofsky. I'm an adjunct professor here in the OBAIS department. And our presentation today is Nammit, the challenges and dangers of casually interpreting ML models. Our speaker is Brandon Greenwell. Brandon is a data scientist at 8451, where he works on a diverse team to enable, empower, and enculturate statistical and machine learning best practices where it's applicable to help others solve real problems. He received a BS in statistics and an MS in applied statistics from Wright State University and a Ph.D. in applied mathematics from the Air Force Institute of Technology. He's also an adjunct professor here, or an adjunct instructor, at the University of Cincinnati. He's a lead developer and maintainer of several R packages available on CRAN and off CRAN, and co-author of Hands-on Machine Learning with R. Let's welcome Brandon.
All right, can you guys hear me okay? Okay.
Yeah.
Pleasure to be here. First and foremost, I know they're recording this talk, or at least they're supposed to, but slides are online too if you want to go back. There's a lot of good stuff linked in this, and good resources, and embedded videos, and all that fun stuff. I'll skip the about me. I should clarify. It's causally interpreting machine learning models. Casually, those are two different things. So, I know, I've had a lot of people giving this talk once before. I think it was like, what are you talking about? So anyway, Reagan in the keynote earlier, I think teed up the intro to this talk quite a bit. She mentioned interpretability and how important it is. She also mentioned how difficult it is to get machine learning models into production. And so I don't think I need to go through and talk about all these and why interpretability, being able to explain these models is important. So I'll just say a couple of things. So we've all models are wrong, but some are useful. You've heard that quote before. So maybe a corollary of that would be all machine learning models are wrong, but some make it into production, right? So, but that's true. All these models are wrong. They don't make perfect predictions, and it's up to us as the practitioners who build these things to understand where our models are wrong and why they're wrong. Are they doing poor in certain subregions of the data? Do they make bad predictions in certain ranges of the feature space? And it's our duty to find out, because a lot of times understanding where these models are really wrong, sometimes we can fix them. And then also it's just common sense. Right? We build these complicated models, we put them into production. At some point, those models' predictions are going to be used to impact customers, patients, the business, drive decision making, and so forth. So we really need to understand, to the best of our ability, how they're making predictions and where those predictions are wrong. I've had a strong research interest in interpretability for probably 8 or so years now. I've written some software about this. And so I can talk about interpretability all day. In fact, when I was first thinking about doing another talk, I was like, I can talk about interpretability. A lot of people do that, so what I wanted to do was talk about one of the core problems I've seen with interpretability over the last several years. Because there's no shortage of interpretability techniques to machine learning. It's now an open, active area of research with generative AI and LLMs. And so it's still a pretty hyperactive area of research, and along with the methods, there's no shortage of good software too. This wasn't the case 8 or 10 years ago. And so interpretability methods are built into open source tools, they're built into proprietary tools, which is a good thing. They're all over the place. And so data scientists who have to build these machine learning pipelines have the ability to easily sort of disentangle the model's logic and try to understand how it's making its predictions. That's a good and bad thing. I tend to use the terms interpretability and explainability that synonymously. I feel like most people do, but in the literature, they do try to make a distinction between interpretability and explainability. They're not very consistent definitions, but I'll say interpretability tends to be the higher bar to reach. We can explain how any model works. It doesn't matter if it's a neural net, deep learning model, random forest, logistic regression. We can explain using the same tools how these models are making predictions. That doesn't mean it's going to make sense to human experts, or we understand like why did it predict so high for this customer and so low for this customer. So things can be explainable, but not necessarily interpretable. But I do use the two terms that's synonymous. And then when we talk about interpretability, we can talk about different levels of interpretability. We can explain a model at the global level, like what variables are driving this model's performance. How does each variable impact the model's predictions when we manipulate them? And then we can drill down all the way to individual predictions, right? From everything like Shapley values and Lyme and so forth. We can actually try to do a good job to explaining how a model made an individual prediction compared to some average or something like that. And then we have black box versus glass box models. I don't like these terms very much, but I think it does help the conversation. I'll say, glass box models are just models that have a bit more of a naturally interpretable structure. Just a progression, a linear model, a small decision tree, right? Those have a naturally interpretable structure. You can easily gauge what's important, what's least important, how the model is making predictions. And then you have everything else where you can't easily, there's not like a prediction equation for like a random forest. And so we usually have to rely on these post hoc techniques to sort of disentangle the logic and understand how it's making predictions. And so that gets into these model agnostic procedures. These are procedures, and we'll talk about some today, that can be applied to any model. As long as you can generate predictions from a model, you can use agnostic procedures to understand how it's making these predictions. And like I said, lots of good software out there. If you're interested, a lot of good resources. These are three that I reference quite a bit. If you're looking for one just to kind of really get into this space, the first one by Christophe Monard is a fantastic book. It's on its second edition. It was arguably one of the first books in this space. And these are all free to read online too, if you want to apply an extra copy. All right, so now I'm going to jump right into the problem, or many of the problems of what's wrong with causally interpreting machine learning. Right? And a lot of it really boils down to the fact that these models are typically applied to happenstance data that we just happen to have. They weren't collected under some controlled conditions or experimental design or anything like that. And so it's observational in nature. And this is a, let's see if this will work. This is a video I play for one of my regression classes that I teach in this room. So it's nice to actually see people sitting in the chairs. So this is a quick 4-second video. I'm going to play it first, and then I'll play the slow motion. Hope the sound works too. Okay. Everybody catch that? All right, so let me play it one more time. Playback speed. Here we go. All right, cat on the bed. There we go, cat in the back jumps. All right, so the question is, all right, so other than the title, what caused the cat in the back of the room to jump? Cat sneezing, right? Do you know that for sure? Can you prove it? All we see in the video is cat sneezing, and then there's a cat behind the bed that just jumps, right? So event A happens and event B happens, right? So there's a term we give to that fallacy. In this case, it probably is true, but is there any other possible explanation for why the cat in the back jumped? Could have been a mouse at that exact time that snuck up, tapped him in the butt, and scared the cat. It happened at the exact same time. Is it as likely as the cat sneezing causing that? No, it's not. So you need good domain expertise and intuition to really carry forward with good causal inference. You can't get it from the data alone. Full screen. Okay. And we've all taken stats, hopefully, at some point. You hear this some form of this term, correlation doesn't imply causation, association isn't causation. Sure, but that doesn't stop people from drawing causal conclusions from correlational statements and associations. It's naturally part of our DNA. We do it all the time. And I'll show some examples later. There's a lot of fallacies that kind of describe the situation of us doing that, right? First one is something called rooster syndrome. It's kind of like the cat video. We see event A happen, and then we see event B happen, so we tend to think that A must have caused B, right? And so, by the way, the term rooster syndrome, I think, comes from an old 1910 play about farm animals and a rooster that believes their crowing causes the sun to rise every morning. So that's the whole play. It doesn't have any sound. It's kind of boring. Modern version is Rockadoodle, if you haven't seen that. It's a very mediocre movie, but Like Elvis and Roosters, and then there's also just spurious correlations, right? We've seen those before. Classic examples you've seen probably plenty of times is ice cream sales and shark attacks tend to be correlated. I never actually looked at it, it's just the example everybody uses. Same thing with shoe size and reading ability, right? These things are just spurious correlations. Usually there's some underlying lurking variable or other variables that are connected to both of these that are driving the spurious correlation. So shoe size and reading ability tend to, to increase together. That's because there's this lurking variable age that's confounding those, right? And these are obvious examples. When you're building machine learning models that hundreds of variables, you don't really have the context to understand what is an obvious just association versus something that's potentially causal, and so it causes a lot of problems. There's some causal fallacies in the wild I tried to dig up. Everything from sensational headlines to just bad research interpretations, and even in media it takes advantage of it too, right? Look what happens when you wear ads versus not wearing ads. All right, so let's drive this home with an actual example. This is an example I took from Scott Lundberg. He's the author of SHAP. I think he works at Microsoft now. So he wrote a really nice little hidden gem of an article a couple of years ago that I came across recently. And they use this example, so I'm just going to kind of steal it. It's important to say that this is a simulated. All right, so we'll come back to that. But this is an example that's not too far from home from the types of problems I help teams with on a day-to-day basis. And so this is like a churn or customer retention example. So the initial goal is to train some model to predict which customers are likely to renew their subscription. And so suppose we have 8 features that we have identified for predicting retention. So the outcome is binary. Did they renew or did they not? So we have things like how much of a discount they were offered, some information on advertising spending on each type of customer, how often they use it, when was the last time they upgrade, number of bugs they reported, outreach statistics, and then local economy information stuff. It's very similar problems out there. All right, so here, build a really complex AI model called logistic regression. Pretty simple and straightforward. This is an additive model. There's no interaction effects or anything like that. This would be an example of a glass box model, right? Whether you've seen logistic regression or not, I've got my coefficients for each variable, standard errors, t-statistics, and so forth. And so it's a glass box model because we have the model. So we know how much each feature contributes to the values and so forth. Logistic regression and similar models have a natural interpretation of the coefficients. Although when I say that, because I don't know who thinks in terms of log odds, but there's a way to interpret them out there for sure. But just looking at this output, if you're familiar with linear models and logistic regression, can you just say off the top of your head which variable or variables look like they're the most influential without even defining influential?
Spend, ads.
Say again?
Ad spend.
Ad spend, what else? Well, let's look at ad spend. What caught your eye with ad spend?
Well, the estimate is for the coefficient, right?
Yes and no. Close. So coefficients can't be used as some gauge of importance, right? Because coefficients are tied to the units of the variable. If ad spend is in thousands of dollars, if I change that to cents, that coefficient will get really big. But some standardized version of the coefficient, so like your t-statistics, right, don't have any units. That's like a safer way of doing it, right? It's a quick and dirty way of kind of gauging. So it looks like ad spend and discount seem to be the largest absolute value in their z-statistic. And then we can look at what seems the least important, and we'll come back to this. But that's good news, right? Because advertising spend and discounts are something that we can control. Right? So nice. Anything else point out as maybe potentially odd or counterintuitive about the output?
Discount's negative.
Discount has a negative sign. It means it has a negative impact on the predicted likelihood of customer renewing their subscription, right? That's kind of intuitive. So yeah. Then there could be reasons like, we look at collinearity and variance inflation factors. There's no problems with that here in this data set. Okay, so let's switch to a more complex black box-ish type model. So here I fit gradient boosting ensemble, so XGBoost. There's no coefficient table with these kinds of models. There's no prediction equation. And so we have to rely on these post hoc techniques like variable importance plots, partial dependence, there's no shortage of methods we can look at. Here's a couple of different variable importance plots. One's based on SHAP, one's based on the tree itself. And again, we see discount and ad spend as the most important features. How they measure importance is different across them, but in general, you'd like to see some consistency. And then, monthly usage and sales calls are down at the bottom. This also is consistent with what we saw in the logistic regression too. Great. Different models, one simple and glass box, one very complex, at least telling the same story. We don't have coefficients, so we might look at something called a partial dependence plot. So this is something that you can apply to any model. You don't want to over-interpret these, but these are like average predictions. So for any black box model, what these are trying to convey is, hey, if I can isolate the effect of all the other variables in the model, what happens to the model's predictions as I vary this feature, right? So think of it as like a generalized coefficient, right? And so again, we look at ad spend and discount, and we see a positive effect for ad spend like we would expect, the kind of counterintuitive effect for discount. That's in line with what we saw with the logistic regression. And this is where I see things start to go downhill in data science. Okay, ad spend and discount are the most influential variables in this model. They have a big impact on the predictions. Great, ad spend and discount are variables that we can intervene on. We can manipulate that, right? If this is saying that increasing discount is associated with a decreased risk, predicted risk of renewing, notice I'm being very careful about interpreting that. Associated, predicted, and so forth. And then vice versa for ad spend. This is where I see that natural leap from interpretation to supplementing that with causal inference kind of happens. As you go back to your stakeholders, you say, hey, ad spend and discount are important. We can manipulate them. And guess what? We can save money by, or we can improve retention by either increasing ad spend or decreasing the amount of discount that we offer, right? And I wouldn't be surprised if this is a real problem, that this information got fed into some optimization problem further down in the pipeline to figure out what's the right trade-off between these two to maximize retention and profits. You can't do that. You can't just causally interpret the output from these models. Here's the actual model that generated that data. A lot of stuff going on here, but the important things to call out are the effect of discount on the actual universal process that generated this data is positive. Look at the coefficient of ad spend. It's 0. So ad spend technically has 0 effect on the outcome here. So what happened? Okay. Translating that back to the plots we saw earlier, here's the actual causal effect in red for discount. It's a small positive effect, not a strong negative effect. And then the effect of ad spend, the actual true causal effect of ad spend on retention is 0. Spending more or less money isn't going to really do it in this fictitious problem. But taking these associations found by the model and inferring something causal from them, lose money, lose customers potentially. And it's not to say that we can't do that, it's just that we have a lot of work to do.
So can I ask a question?
Yeah.
Sorry, I missed where is the causal model came from? How did we build that?
It's the data is a simulated example, so we know what the truth is.
Oh, this is like an actual, if we know exactly what would happen? Gotcha.
Yep, so in real life, we don't know the red lines, right? We just know the black curves, but we have to understand that those can potentially be misleading when you have things like confounding effects and deviators and stuff like that. We'll look at that in minutes. But that's, it happens all the time. Even the experts, world experts, slip up and do this all the time. You may know who this is? No, not Tim Sharani, it's his colleague. This is Trevor Hastings. He's pretty well known in the machine learning in our communities. He was given a talk, it's linked here, it's a fantastic talk on data science. But midway through that talk, he was interpreting an effect plot, not unlike the ones I was just showing to the audience, and doing it using causal language. And at the end of this talk, one of the audience members asked a question about, like, hey, do you normally supplement these, the interpretations you get from these models with causal language, and he said, oh, nope, I didn't mean to do that, and this is literally the second time he was saying sorry. But it's a really good talk. Experts do it. Data scientists from all different backgrounds and skill sets do it. It's a very common thing, and it can be very dangerous if that, causal mischaracterization of the associations of a model lands in the hands of stakeholders or decision makers, and they're inferring causation from it, can lead to some very bad decision making. So then what? Doesn't mean we can't do anything, right? But causal inference is a very controversial topic. There are those who are like, you can't do it, it's design experiments or it's nothing. There are those who think you can use generative AI to do causal discovery. My colleague Christoph is like over here, who's like, you can't do anything ever. And I'm like right here in the middle, right? I'm a healthy skeptic, right? Causal inference is a very rapid area of research. But if you think about, I try not to use the word AI in this talk, but I'm going to say, with AI, how can we reach like true human level understanding in AI without causal reasoning? Right? And right now we can't do that without strong domain expertise and people in the loop. And so in order to actually really do something causal with our data, especially if it's observational data, we need to start with a causal model. I'm not going to play this video because it's 3.5 hours long, but this is a talk by someone named Peter Tennant, who I think is a professor of epidemiology. Epidemiologists know what they're doing in causal inference. They've been effectively using this area of research for a long time, quite effectively for public health and so forth. There's this interpretable machine learning workshop. He gave the first talk, and he just really nails it on the head with some really fantastic points. So definitely worth watching. So before I get into talking about some things that we can do, if we really want to try to make that leap from describing these associations in the model with saying something causal, we need to borrow some language from causal inference. This is by no means a well-rounded discussion of everything you can do in causal inference, but the DAGs usually play a fundamental role. These stand for directed acyclic graphs. So DAGs, in short, are just a way of taking subject matter expertise, domain experience, and encapsulating all those assumptions in a graph. Okay, and it's directed because our causal assumptions, what features causally affect other variables in our data set, are represented by these directed arrows. And it's a really good way of just sort of like capturing in an easy to read graphic all your assumptions and your domain expertise. And that's important too, because a lot of the stuff we do in causal inference hinges on the assumptions that we put forth based on our domain expertise. And a lot of times those assumptions aren't easily verified. So here's an example of a couple of DAGs. Suppose we have some data set, we've got features x1 through x5, and we're trying to predict some response y. Causally interpreting a machine learning model, logistic regression, so on and so forth with causal language assumes a very particular DAG structure. And that's the one here on the left. And what this graph is saying is that x1 has no influence on x2, vice versa. There's no confounding variables that we have measured and so forth. Everything's nice and independent and has a direct causal effect on the response. It doesn't work like that in any situation. Even in designed experiments, it's not always that clear cut. Usually the universe is more complicated, and usually what you have is something like this, and even this is pretty easy in comparison, but this is saying like x1 causally affects x3, same with x2, which affects x4 and y, x5 is in it. So usually it's a more complicated picture of what's actually going on. Think about that example at the beginning, shoe size and reading ability. There's another variable, age, that's affecting both and so forth. Imagine if you have 100 variables. It's huge. That's not huge. There's probably somebody else had like 25,000 variables, right? So usually it's a complicated thing that's going on. But if you can isolate based on domain expertise, which has to be there, what you think based on your experience and debate with other experts, that this is the picture that's going on, this picture can tell you which effects you can actually estimate causally and which ones you can't. That's the important piece. If you have the right domain expertise to put a picture like this together, this picture will tell you what you can and cannot do. Let's see the background. All right, so sticking with that particular picture, again, we have these 5 input variables and some response. So suppose that we put a picture like this together, but we're interested in estimating x3, or at least the causal effect on x3, right? As I change x3, what does that cause in terms of y, right? And this picture tells us that, well, we have two other variables that confound the effect between x3 and y. x1 causally affects x3 because it has an arrow pointing into it, and so does x2. So these are examples of confounders. Confounders have the ability to cause spurious correlations between the variable you're interested in and your outcome. And so you have to adjust for those appropriately in your analysis, okay? And then you have, so again, we're interested in x3. x4 isn't a confounder, that's what we would call a mediator. So x3 impacts x4. And so with x3, we can talk about, well, what's its total causal effect, right? So the effect that x3 has on y plus any indirect effect it has through this mediating variable x4, and so forth. Okay. And I've got an example of the actual example that shows some of these different variable roles that we can have in DAG and what the ramifications are later. But the idea is that you have to be able to have some kind of causal model based on assumptions. And depending on what that causal model looks like, will help dictate how you can estimate causal effects and what you can and can't do. So for example, if we wanted to estimate the direct effect of x3 on y, we would have to adjust for x1, x2, and x4. And learning from these graphs what the appropriate adjustment set is for different variables can be a pretty challenging thing to do. Fortunately, the mathematics is there, and this is automated through software. So tools like DAGs and stuff, as long as you can put forth a good graph based on strong domain expertise, tools can tell you, like, hey, if you want to estimate the causal effect for this variable, you need to adjust for these. Or it'll tell you you can't because you don't have right information. So there's an example. If you come back to the slides, you can copy and paste this into DAG and you play around with it. You can assign variable roles to have, I'm interested in the causal effect of x1 on y, what do I need to adjust for, and so forth. And again, causal inference, huge, scary topic, active area of research. Here are some really good resources that I've found useful. Mixtape, there's a lot of Jay-Z quotes, good book. And then this one's also free to read online, so you don't have to actually buy it. So it's a really good resource. All right, so back to the retention example. Here's the actual DAG. Okay? In this case, this is the actual DAG that helped generate the data of the simulated example. But this would be the DAG that we would want to, as a team or whatever, based on debate with other subject matter experts, try to hypothesize. Hey, we think that sales calls obviously has an effect on the number of interactions we have with the customer, because every sales call is an interaction, but we might have other interactions too. And the number of interactions likely impacts whether they renew or not. Discounts, so on and so forth. These dashed circles are variables that we think influence the other variables, but we don't have any way of measuring. What we would call, in this case, unmeasured confounders, because they affect other variables and response. And so, again, it's not just about putting forth your assumptions for the variables that you have, but also the variables that you don't have that you think could also be influential in this particular system. So if we had something like this tells us what we can and can't do. This tells us that we can't actually estimate the true causal effect, either direct or indirect, of discount because we can't account for this unmeasured confounder. So there's really nothing we can do with this. You could maybe try to design an experiment or something. But ad spend we can, because it's confounded by monthly usage and last upgrade. There's no other mediators. And so if we wanted to actually estimate the causal effect for ad spend, we don't just throw all these things in a regression model or a random forest and look at these plots. We have to account for the variables that are actually confounding it and nothing else. And so I was really interested to try this method that I saw in a paper a few years back. So this is also by Trevor Hasty and one of his colleagues. So they wrote a paper about, so he should know better about supplementing interpretations of causal knowledge. This is a really interesting paper because they established a connection between partial dependence, this very common interpretability technique that's built in software all across the board, and the methods in causal inference. And so I'll skip the math, but the connection is that the actual, in theory, what a partial dependence plot is estimating in terms of the effect of a variable in response, is mathematically equivalent to this famous backdoor adjustment formula by Judy and Pearl, who's really well known in the causal inference circle. And so the short of it means is that under certain very specific circumstances, you can in fact interpret those partial dependence plots causally. The trick is like, what are those certain conditions? And so it just happens to be that that adjustment set that I was talking about. So given a DAG and a variable that you're interested in trying to estimate some causal effect on the response, there are ways to pull off like what the appropriate adjustments and what variables do you need to condition on appropriately to actually infer something causal. And as long as you have that, then you can rebuild your model using that, just that appropriate. So instead of using all available input information, just use the adjustment set that was identified by some tool, and you will get a partial dependency plot that should estimate the actual true causal effect. And so we know that that ad spin should have zero causal effect on the outcome of interest. So I was really impressed that I put this in and it didn't work. So I did this like 3 weeks ago. I'm like, this is going to be a really cool example. Nobody's read this paper, and people should be using this all the time. And so I thought about taking this example out. And I thought about just trying different models until I got one that worked. That's all very unethical and not very good. But I thought about this for a long time. Like, why is it doing this? I've got data that I know in theory what the actual DAG is. I know what the adjustment set is. I have in theory a procedure that estimates the causal effect under these perfect conditions that I know are met because this data are simulated. Why on earth is it still giving me a positive effect?
Is it a collider?
Say again?
Was a collider in the deck?
Not a collider, collider is another role a variable can play. Collider would be an example of a variable you do not want to adjust. So that's a good call out because again, it's not just putting everything in your model. There are variables you should adjust for. There are bad controls, and then there's like neutral controls.
Yeah, because there was no direct arrow from expand to. I remember I saw when we put a DAG up there. Was it discount or expand that didn't have a?
That was discount.
Oh, sorry.
So adspin, in theory, we have all the information we need, and I'm using it right here. So the best I could come up with is maybe it's a case of estimand versus estimate. What I mean by that is, in theory, that expected value that we're estimating with a partial dependence plot has a causal interpretation under the conditions that are met in this particular analysis. But the estimator that we use to actually estimate a partial dependence plot, that's what's rigged up in all the software you might use to employ some of these tools, assumes that all your features are completely independent. So there was a nice paper that came out, and a lot of the common interpretability tools you'll see, like permutation importance, different flavors of Shapley values, ice curves, partial dependence plots, are all members of this, what we would call permute and predict methods. And they can be frowned upon, especially if you've got correlated data. They can be very misleading because how they're constructed involves you randomly shuffling feature values around. And if you've got things that are correlated, you kind of break that correlation structure. And so the short of it is a lot of the interpretability tools out there, for as great as they are, everything kind of breaks down when you've got correlated data. But when you're doing causal inference, correlation doesn't imply causation, but it is circumstantial evidence of a cause. And so when you have cause and effects, there's going to be correlations. But we have a method that we can't use with correlations because it kind of breaks down. So it's kind of like a double-edged sword. So in theory, it's nice, but the way it's implemented doesn't work. At least that's the conclusion I came to. And so interpretability is really hard. There's a lot of work to improve these methods, especially in the presence of correlated data. If you've got correlated data, it becomes really hard to tell an accurate story about what the model's doing, whether it's causal or not. Let's get this for who's heard of double machine learning? Well, at least, it's like the hip thing on the street right now in causal inference. It reminds me of like when deep learning came out, and everybody was like, I'm going to deep learn this, I'm going to Keras that. And when it comes to causal inference, because people kind of think it's like a golden hammer, it doesn't have any assumptions. And I've heard in a couple of conversations, people use the term double machine learning in a similar way. Well, like we'll just use double machine learning to get around, having a DAG and stuff. It doesn't work like that. It has the same assumption, but it is an effective tool. So double or debiased machine learning is it's not a brand new idea. It's been out for a few years, but it's starting to catch on. And at least in my industry, where people are doing causal inference. So when I said having an adjustment set so you can know, whether you can estimate causal effects, there are a lot of different ways to take that information to estimate that causal effect. I showed partial dependence plots. There's other things out there like matching, propensity score matching, difference in differences, instrumental variables. There's a lot of different techniques, but they all, for whatever reason, rely on the same assumptions. And double machine learning is no different, but it breaks the problem up into two machine learning models, hence the name. And at the end of the day, you get an average effect estimate, but it still requires, forget the outer, it still requires that you have an adjustment set. It doesn't get you out of subject matter expertise and having a DAG, you still have to have that. But in this case, it did a much better job than the partial dependence approach did. Using the same adjustment set, now I get a causal effect that's somewhere between -6 and 0.4. So there's not a whole lot of evidence to support that effect is actually any different from 0. And so but that's a method that's out there now. It's starting to catch on. But the one thing, if you get roped into a conversation with double machine learning at some point, it's not a gold mine. It still requires the same inputs, the same subject matter expertise, the same unverifiable assumptions, and so forth. And it's not something you can just scale to. All right. Design experiments. I'm going to go quick because I had my 10-minute mark. Don't get enough credit where they're due. I come from stats, so of course I grew up with design experiments to some extent. But design experiments are still considered the gold standard for inferring cause and effect. But again, like in different industries, they're prohibitive for different reasons, either ethical concerns or they can be expensive. However, at least in terms of the latter, machine learning and interpretability can help at least focus in on a more narrow hypothesis space so that you can feasibly conduct an experiment if you need to understand cause and effect. And so I'll quickly just go through an example from a talk I went to in grad school. This example resonated with me ever since. It's a talk by Dick DeVoe, one of the best speakers on data mining. He was talking about a consulting project where he was brought in to help this company that makes these large metal ingots. I think they're used in the manufacturing of like aircraft parts. But these big metal ingots, after production, started to crack. And they had like a 20-25% cracking rate. And every time they're cracked, these parts get used in airplanes, so you can't have cracks. They got to recast them to where they're perfect, and it's really expensive. So they were hired on to say, hey, we've got all this historical observational data on past ingots, ones that cracked and didn't, and then all the the inputs that went into making them. Why are they cracking? It's a causal question. Okay? Why or what is causing them to crack? Okay? And so a lot of back and forth, a lot of iterations. It's a really funny story if you go back and listen to his talk. It was linked there. But they ended up with a very simple business rule based on a glass box, a very simple split decision tree that showed chromium was a good differentiator between those that cracked and didn't crack. It's just pure interpretability and association. But they went back to the engineers and were like, well, maybe it's chromium? And they kind of went, huh, that could make sense. And they designed a follow-up experiment and actually determined that actually was the primary cause of that cracking. So interpretability at least led them to a hypothesis that they can actually go test in a not as expensive way instead of looking at 149 different variables. So +1 for. Last example, even if you're not doing something causal, all models are wrong and they end up in production. Sometimes where models are making mistakes, if we understand where they're making mistakes, sometimes we can fix it. So the last example I'll give you is this hospital admission example where patients were admitted to the hospital with pneumonia. They're trying to understand who's at risk of dying from pneumonia based on things like various patient demographics, white blood cell count, lab tests, checks, X-ray information, 46 features in total. And the goal is to predict the probability of death, dying from pneumonia. Here is one of those partial dependence type plots that shows the effect of age, which is the most influential variable in our model. So as you would expect, the older you are, the more at risk you are of dying from pneumonia. And then once you're past 102, do better. The case, right? This happens all the time in these models where you don't have a whole lot of data in this region, and the models can do all kinds of weird things. This model is still doing this in production. It's still going to predict a lower risk for abnormally older patients. right? And so that's an example where you don't want them. And so this would be where we might want to put a constraint on the model saying like, hey, based on domain expertise, we know increasing age causes a higher risk, so we might force that onto the model. Here's another one for the second most important variable in that model, whether or not they had asthma. Doctors know asthma is a risk factor for a high risk likelihood of dying from pneumonia. But the model says that if having asthma severely lowers your risk. Okay? But again, so the analysts in this particular example went back, talked to doctors, like, hey, what's happening here? They're like, well, we know that if you're admitted into the hospital with pneumonia and you have asthma, we know you're at higher risk, so we'll put you on a more effective and advanced treatment. So what's happening here, so I went back to this example and I was like, well, let's think about this from a causal perspective and what a DAG would look like, right? So we have an indicator for asthma. We have it influencing the risk of dying from pneumonia. But now we're saying that like patients who have asthma are likely to receive better treatment. And that better treatment plan also has a different risk or an impact on the risk for the patients, right? And so this would be an example of something called a mediator, right? But this is an example where all the people in this particular data set likely, if they had asthma, only go through this particular path, right? So there's kind of like almost like a survivorship bias kind of thing happening here. And so what this means is that we don't have any information on this variable. So we can't actually estimate the direct effect of having asthma. We can only see what's happening as it's mediated through this additional treatment. And this treatment is effective enough to actually flip the sign of what's actually happening. But again, it's wrong for the model to make these predictions for these patients. And so it's wrong for us to put that into production. And we know having asthma causes you to have higher risk of dying from pneumonia. And so that would be an example where, again, we would want to delete that effect. And you can actually go in and edit models, right? And I'm not saying like you can just erase regression coefficients and write in whatever you want, but certain models lend themselves to being able to be edited post-production. If you can't go back and refit that model with proper constraints, tools like GAM Changer can be pretty useful tools for doing that in a safe and reliable way. Causal discovery, I'm at time, but I'll just say that's a big area of research right now. Not going to happen anytime soon. You cannot take the domain expertise out of the equation. Causal discovery through generative AI and other ways can help iterate towards a good DAG structure to start with. But again, you can't take the human out of the loop here. And then I'll end off with just a couple of key takeaways and some quotes I like. Again, machine learning models aren't designed inherently for doing causal effects. They're designed to take advantage of correlations and associations to make potentially accurate predictions, and that's it. Sometimes we can do stuff like, again, the partial dependent stuff that works, so maybe don't use that. But causal knowledge and subject matter expertise can at least still be used to improve these models and make them safer to put into production, putting on proper constraints, but that you still have to interpret the model and understand where it's making mistakes. And so 2 quotes from Alex's book, who's sitting in the front row, that I really like, that I think convey how I feel about causal inference, is that it's not impossible with observational data, but you just really have to know what you're doing. You need good domain expertise, good strong assumptions, and the use of clever methods like double machine learning and so forth. But whether all that's there and all those boxes are checked, you should be skeptical of any causal inferences.